Thanks very much for the introduction. So I'm Thomas. I'm one of the principal data scientists at a company called QuantumBlack. We are a data science consulting company. We're owned by McKinsey, but we operate in a number of different industries. So I do a lot of work in like the banking industry, the pharmaceuticals industry. But today, what I really want to talk about is a project I did a while ago already for an elite sports team. And yeah, I want to give you a bit of a flavor of the kind of work that that we do and how you can sort of apply data science in an industry that you might not hear of often when people think about applying data science to. And specifically, I want to talk about some of like the key challenges that we kind of saw in this project and how we overcome those. So how this kind of starts and how most consulting projects start is you come to like an organization. Often they're not very data savvy type of organization, so they don't really know yet how to frame like a data science project or problem to you. So they come to you with a very broad question, So in this case, we went to like an elite football team. Think like a team like really in like one of the top international leagues, and they come to you and they say, we have all this data about our players. But our players get injured a lot. And this is like a really big problem for us because when they get injured, they can't play. We lose matches because our most important players like can't play anymore. They also lose money on like sponsorship deals, for example. So there's like a lot of like financial incentives as well for teams to really have players that don't get injured often. So they come to you with this big question, and you might at first glance already think, okay, this is like relatively well scoped, but it really isn't. So when a person or a company comes to you with a question like this, you should really think about, we always think about all kinds of sub-questions that come up. What does it mean? What type of injuries, for example, are we talking about? There are different types of injuries, like contact versus non-contact injuries. What that means is a contact injury is when people like really bump into each other, and then as a result of that, one or more players get injured. Or non-contact injury is more something, that happens because of fatigue or like wrong technique of a player. So there's stuff like that. You can think about, okay, do we want to focus on specific players? Are there specific players that are more important? Often the answer to that question is yes. There are star players that you really want to be sure of that they don't get injured. The fans like to see them play. And you can also think about, okay, do we only want to do this for the players that we currently have in the team? Or do we also want to think about prospective players? When at the beginning of a season, a team is going to draft new players, they want to hire players that don't get injured a lot. So all these kinds of questions like usually come up when you get like a broad question like this. So what we did over the course of a couple of months with like quite a big team, so think a couple of data scientists, a couple of data engineers, a project manager, and also some doctors. What we did is we built a predictive model that would diagnose players that are of high risk of injury. And what we did is this technical team, we worked alongside the team doctor and the team trainers for quite a long period. And we focus only on lower body non-contact injuries. The reasoning being, contact injuries is just really going to be hard to predict when people are going to bump into each other and hurt each other. So we're going to focus on those injuries that we can maybe catch because of, bad technique, fatigue of a player, this kind of stuff. And what we did is we combined a bunch of different data sets corresponding to like the medical data of a player, specific player characteristics, but also like gameplay data. So what a lot of the players have, they have like these kind of wearables, and these wearables, they track their movement, the players' movements on the pitch. So you get like 10 times per second, you can sort of get their XYZ coordinates on the pitch. So you actually get like a really, really big data set of like player movements for you as well. So what we did is we in the end built a machine learning model. It says here we trained it on 27 predictive variables, which is true, but this is coming from like a really, really big data set. So there's like a lot of like feature selection and data mining happening before we get to those variables. And we're going to talk a little bit about that as well. But first off, so knowing that this is now the problem, right? We're going to predict these players that are of high risk of injury. How are you really going to do that? Because there are different kind of ways in which you can frame this problem, in the sense of framing it as a machine learning, like a statistical problem, right? So one thing you can think about is framing it in the context of like a survival analysis problem, which means you're going to predict for each player what is the time until the next kind of the next injury. So that's one way you can do this. You can also see this more as a classification kind of problem, like which player is going to get injured. Then you get a bunch of extra questions, because then you suddenly need to think about the time frame. Are people going to get injured in like a week, a month, a year, next match? Like what is then your time frame going to be? If you've done like churn prediction in the context of classification, you'll see that the questions are like very, very similar. So this is kind of where we start as a data science team. We're going to think a bit. We're going to do a bit of research. And in the end, we decided to kind of frame this as a binary classification problem. So quite a classical context. So what we did is we looked at all the data sets, we combined them all together, and we created this one big set, this consolidated data set, where every row corresponds to one player, what we call a player day. So basically, all the players of the team, we're going to track them over time. Then we're going to have all these data sets that describe, a player up until that point in time. And what we want to do is we want to predict what we call the target variable, which is this player going to get injured in the next week? And you can kind of imagine that then this is something that a team doctor or a team trainer can then act on. They can change like the training schedule of the player. They can take them out of play entirely. The different kind of things is basically what the team can then do. So what I want to talk about is some specific components of the project. So this is kind of like, this gives a high-level overview of roughly all the different steps, that we sort of went through in this project. And I think you'll see that there are quite standard steps in what you could consider like a data science project. There's a bit of a lot of data engineering, cleaning and integrating the data sets. Then there's a part that's more algorithmic, where we're going to think about like, okay, how do we do the feature selection? How do we do the cross-validation? How do we train the models? And then how do we actually use the models at the very end? What is tricky about this problem is the following. So you actually have a lot of different data sets, because you have this tracking data set, you have the player characteristics data set, all this kind of stuff. And especially the tracking data sets can really be terabytes big. But that volume of data doesn't actually tell the whole story, because when we think about this classification problem, we're gonna try and predict whether somebody's gonna get injured. So how much you can like learn from injuries is all going to depend on the number of injuries you actually have in your training data. And this is like the real problem, because people don't get injured that often, and there are not that many players in the team to begin with. So we looked at like 3 or 4 seasons of data. And in that kind of data set, you can reasonably expect to see maybe 50 like lower body non-contact injuries. So really actually not a lot of data if you think about it. So one of the key things, or two of the key things in our project were actually, one, feature engineering, because you now have to be really smart in how you build your features to reliably like pick up the signal from the few observations of the target variable that you actually have. And then the other part is your feature selection kind of mechanism. This needs to be a really robust algorithm, because there's going to be a lot of like noise in this data set, and because you don't have a lot of observations to actually learn something from, this needs to be quite a robust and stable method. So I want to talk a little bit about these two things in the talk, because I think it's quite interesting, and I think this applies generally to many data science projects. A lot of the gains is not necessarily going to come from the fancy machine learning model you put on top. It's about the foundationals, about the fundamentals, I mean. You need to think about your feature engineering, really think about the domain, and you need to really make sure that you don't, this kind of like approach where you just put a bunch of features into a model and just kind of let the model like hope that the model figures out what's going to happen. Can work, doesn't always work, and especially in like low sample size problems, not a winning strategy in my experience. All right, so how do we do that, right? Because we come into this new project in this new organization, and we have now defined the problem. So how are we now going to go about that? And the way we kind of do that is we usually take a very hypothesis-driven view. And what that means is like we as a technical team, we kind of sit down with like the business stakeholders, the team doctors in this case, and we're really going to list out like a large number of hypotheses around, okay, what could actually drive the risk of injury for a player. And so we do multiple like expert interviews with like other teams, other doctors that we see, and this really helps us kind of wade through the data environment, because when we came here, you really have 30 different types of data set, each with, again, like, from 10 to 100 different variables in it. So it's really, you need some kind of like compass to guide you through the data environment. And the way we kind of do that is through this like hypothesis-driven view. Once we have those hypotheses, we can think about, we can actually look at what we call the data landscape, which is really like, what are all the different data sets that are available in this organization? And for this specific team, okay, this is quite a complicated like slide. I'll spend a little bit of time explaining it, but not too much. So really the way you should read this slide is as follows. So each like little bubble here is a data set that we had access to. The further away from the center the bubble is, the more frequent this data set was updated. So you can see, for example, at the bottom, you'll see a lot of data sets that have to do with player tracking, because this is data set that you get actually very, very often. There's also something here at the top left, maybe you can see it, there's a data set called wellness monitoring. What that means is after every sort of training or every match, these players, they get like a questionnaire that they have to fill in, and it's all about their self-reported like, their fatigue, their mental well-being, like these kinds of things. So these teams collect a lot of data about their players to understand what's happening. And the bigger the bubble, also like how many like the more variables we kind of extract from that. So you can see quite a big, like complex, like data landscape. So what do we do then? We take our big sort of list of hypotheses that we have thought about. We take this data set and we prioritize them. We think about, okay, which hypothesis do we think is really gonna be? Do we a priori think is gonna be have the highest sort of impact or value to look at? And then step by step, we kind of like go through the data landscape, integrate these data sets into a proper, nice productionizable data engineering pipeline, so that we can then look at those in the context of a data science model. And what I want to do is think a little bit, like basically go through like an example hypothesis with you to sort of tell you how that process kind of goes and how important it is to really think about the domain and to have frequent like interactions with your stakeholders. Especially, again, in like non-data-driven organizations, this is really something you want to keep doing. You want to keep coming back to them, validating whatever you're building, whatever you're finding with them to see if that really makes sense. So, question, what data set would you actually look into first? We built a lot of hypotheses. We also talked to some other professional, like sports players and doctors. But you might be able to guess it. Like one of the data set that we thought was really of high value was this player tracking data set. What is like does player like movement, these kind of player characteristics drive the risk of injury somehow? So this is the kind of data set that we're going to look at right now. And like one key hypothesis that we had was the following: we thought that players who are at high risk of an injury may show fatigue, and that fatigue is manifested by them running or sprinting at much lower speeds. So what do we do? This is a hypothesis. We're going to get the data, and we're going to build like variables that try to like reflect this hypothesis, right? And basically test that into our model. So the way we kind of did this is we took like a game or a training session of a team, and we split that up in a number of time blocks. So we split it up in 6 time blocks of 50 minutes each. And then we computed different kind of features that would describe a player's like movement profile in that specific session. So for example, here you would have player number 14 on day 1. They would play a trading session perhaps. We would have 6 blocks of time, and we would record the maximum speed, their average sprinting speed, the number of seconds they played, a measure called a measure that measures your heart rate, like these kinds of things. And we then aggregated those entries because that's what we need to do. Remember that the original layout that we had was not on a player by day by block of time level. We wanted to build a data set that had 1 record per player per day. So we take all these blocks of time, we build these features, and then we apply a bunch of like aggregation transforms to then get it back onto like a player day kind of level. So you can see, for example, here we take the sprint speed feature, and now we compute the mean across blocks, for example. Or we take the mean of the maximum in each block, for example, as well, of the max speed. So this way you can build quite a large number of features, you can imagine, because you can look at speed, acceleration, maximum, minimum, you know, you can go quite nuts with this stuff, trying to sort of characterize what a player's movement actually is looking like. So this kind of worked. But the performance of the model we got with these kind of features in it was still not really what we were looking for. So it captured some behavior, but we didn't feel like we captured really everything. So what we did then is we will go back to our business stakeholders, we talk about the results, and then we think together about, okay, maybe our hypothesis was like not correct, maybe we missed something. And then once we did that, we kind of like specified our hypothesis, like we added like a little bit of detail to the hypothesis, which is we changed it to, okay, let's say that we think that players who are at high risk of injury, they may show fatigue, but that fatigue is not just manifested by like lower speeds, but it's manifested more through like inconsistencies in their movements across the game or across the session. So knowing that, or taking that hypothesis further, we started to build features that would reflect these type of inconsistencies. So instead of only looking at, again, like the means of the average speed across blocks or the standard deviation of speed across blocks, we would also compare different time blocks against each other. You know, we would look at the first block of a player and compare that to the last block to really see, is there something happening to a player's like type of movement over the course of the game. So already this helped, but I just want to like go through this example to really illustrate like how powerful this was. So the numbers are made up, but it's like an illustrative example of what actually happened in this data set. So what I'm showing you here is a variable we call it sprint ratio for 6 different time blocks for 4 different players. So each bar here, each colored bar is a different player. And what I want you to focus on is the third bar, the big blue bar in each of these blocks, because this player is actually about to get injured. So if you look at this profile, you might already see that, yeah, if you just take the mean across time blocks, that's not going to be like super informative. You know, the first one is maybe a bit bigger, but if you look at the other 5 ones, that's all about the same. So like, yeah, a mean kind of measure is not really going to capture that kind of behavior. But if you look at it, you see, if you look closely at this, you actually can see that something weird is happening. Because if you look at the first block, first 3 periods, this player is sprinting at a much higher ratio than the other players in the team. And then in the last 3 time periods, they're actually like much lower, sprinting at a much lower ratio compared to the rest of the team. And this is kind of like a hint, you know, that you can only find by really thinking about the problem and diving into the data. So what this kind of told us, okay, we shouldn't just look at like the behavior of players. We should look at relative performance. We should look at the performance of a player against the rest of the team, perhaps against other players, also against themselves, because you can see there's some kind of downward trend, and see if this kind of helps us capture these kind of irregularities in a player's movement pattern. So this is exactly what we did. What we did is we look at the player, and now we compute, instead of taking raw features, we just use simple z-scores. Sounds very simple, but was actually very powerful in this type of stuff. And I think this is a general observation from working in many different data science contexts. Sometimes like simple stuff that's powered by very fundamental domain knowledge is a lot more powerful than just using a very fancy algorithm and just giving a lot of data. And the same happened here again, because if you then start to look at these z-scores, which try to measure like how far away a player is perhaps from some kind of mean, and that mean maybe it's like the player's own performance or the performance of the team, you can really see that, especially if you then normalize this value compared to the rest of the team, for player D, this value is much, much higher than for the other players. So this is like this was a very important feature for us, by the way, that really helped us understand the difference in behavior between different players. So this was a very key observation in the project, and we used this to generate a lot more hypotheses around behavior. So we started to look a lot more around relative performance of players. Of course, we still had these like minimum speed and max speed like features, because it still gives like some context of like how a player generally behaves. But we really wanted to capture these inconsistencies, which we did by looking at we looked at fatigue or inconsistency across time blocks. So like I said before, we would compare first time block against last time block, Or we would look at the performance relative to the team. So then we would perhaps, compute the average sprint ratio, compute for each player, and then for a given player, compare that to the average of the whole team. Or we would compute this relative to the player themselves. So then perhaps we would look at like some kind of time history, over the last 3, 4, 5 games. This is the average sprint ratio, and now you can see it's like trending downwards or trending upwards or something like that. And finally, we would also look at the role a player had as well, because you can imagine that when a player plays defense or when a player plays offense, that is of course is going to have a very different kind of like behavior, like player behavior associated with it. So that's also quite important. And you can then again you can use that to create many different features. One such example of a feature I've displayed here. Because the challenge with building but the challenge in this project was that, okay, we found this kind of like nice sort of insight into the data, if you will, but it was quite hard to explain this to very non-technical people, because we're talking to doctors, to trainers. These are really people that don't necessarily have a statistical training. So even if you talk about the mean of the standard deviation of the max or something like that, then you've lost everybody in the room already, right? So we really had to take it easy and like really step by step explain these things. I can talk more about this later, but I just wanted to illustrate like one example of like a complex feature that you can build that really tries to capture inconsistencies in a player's behavior. So this is how we in this project can approach this feature engineering type of work, and this is also quite typical of like how we at QuantumBlack do a lot of our work. It's very hypothesis driven. Very much we talk a lot to our stakeholders. If you get into a new domain, we call subject matter experts either in the company or externally, and we try to like bake that expertise into our data and into our models. As you might get a feeling for this already, because I talked a little bit about like the large number of different data sets and all the different kind of features that you can build from that. And if you marry that with the fact that, we actually don't have a lot of observations of our target variable because the number of injuries is actually quite low, you can see that there's a bit of a problem there, right? Because like somehow you need to sift through all those features to build a model that's actually robust, stable, and in some way performant too. So a big part of this project, besides feature engineering, was the feature selection type of work that we did. And I just want to spend a little bit of time on that because we used an algorithm that is actually quite common in some fields of statistics. So if you're a geneticist, you might have actually heard of this algorithm, but I've not seen this one mentioned so much in like classic data science literature on like feature selection. So we used a method that's called stability selection. And this is used a lot in high-dimensional statistics, like genetics, because there it's the same kind of deal. You have thousands and thousands of features and only a couple of observations. And somehow you need to learn what genes are, relevant for the thing that you're looking at. The idea is you take like a base learning model, which is often like a lasso type model that already does some feature selection, right, through the regularization. The thing is, in low sample size problems, is that you need to tune this hyperparameter, right, the regularization parameter of a lasso model. And in low dimensional like samples, and especially if we also then have class imbalance, this tuning of this parameter becomes very noisy. So you can sometimes get in some kind of like suboptimality just because of the kind of data split that you're using. And kind of like what the stability section does, it wraps around another algorithm. And what it does, it takes the original data set, it generates many different like bootstrap samples of the original data set, and then estimates lasso models on each bootstrap sample. For many values of the regularization parameter, by the way. So there's no tuning of this regularization parameter in this procedure. And what you then do is you just track for every original bootstrap sample, does this feature ever get selected by any of these lasso models? So you do that for every bootstrap sample that you have. So you basically, for every data set, you're going to get, for every feature, does it get selected at least once, yes or no? And then you can compute the fraction of times a feature gets selected in every bootstrap sample. And you can show that this is I'll link to the paper later, I believe. You can show that this sort of corresponds to like a probability of whether this feature gets selected by the model. So it's some kind of like probabilistic measure. And so this is this posterior probability of inclusion at the bottom. And you can then use a cutoff on that to select, a set of stable features. And the idea is that you only select a feature if it shows up in many different bootstrapped samples of your data, and what bootstrapping just does, it's perturbing your original data set, right? So it just adds a little bit of noise. So what this really is saying is, I'm only going to keep variables that show up in many versions of the original, many versions of the original problem that are a bit changed. So if the relationship between a feature and the target variable is strong, it's going to survive that statistical noise that I add to it. And if it's weak, then that noise is going to kill that relationship. So that's the intuition behind this. And we've seen that this works quite well because this data set is so noisy, and this is very stable. This is a very harsh feature selection method. So if you apply this on a lot of standard data sets, you'll see that it typically selects very few features because of this. But in our context, this is exactly what we want, because for a model like this, we really only care about truly about the features that are important. The nice thing about this is, so if you're an R user, you're happy days. Statisticians love R, so there are many implementations of stability selection already available. In the Python world, there are less implementations available. However, it's actually quite easy to code up this specific algorithm, because like I said, it's just generating a bunch of bootstrap samples, fitting lasso models, and recording what gets selected at what times. So really, like you can see, the naive way to do this, would be to do this double loop, like I did here. You loop through different values of the penalization parameter and through different bootstrap iterations. And then you fit the lasso model and you just keep track of what's happening. Highly recommend to give a look at this specific algorithm if you're dealing with a similar type of situation. So that's kind of what I wanted to talk about. So all this work over, I think it was a period of 20 weeks, kind of culminated in this kind of dashboard that was then used by the doctors. So you could see the sort of the risk score for every day for each player. And then we also used explainable AI techniques to really explain, how does this feature relate to this prediction we made. And this, by the way, doctors found very insightful, because it really brings it a bit to life, right? And yeah, so in the end, we managed to make this work. I can talk to you a little bit about the precision and recall, because you can imagine there's a big trade-off between precision and recall on these things. Well, especially there's a big question around your false positive rates, because you don't want to flag people too often. So many analysis we did on that as well. But really, what the nice thing about this was that this thing did this work. So one very powerful thing that we showed was, in one of our last meetings with our client, was we actually showed the risk profile of a player. And this was their star player, actually. So they anonymized the data, but the thing is it's very easy to tell because you have so few players, who is who. And you can actually see that this player gets injured at the dash line to the right, and then we flagged that 2 weeks before, and this was super, super powerful, really brought it to life. So yeah, so this is what I wanted to talk about. Thanks very much for your attention.
Yeah. Plenty questions, so I have to take maybe just a few. I'll try to put these two together. How many different types of sports do you cover with this approach, and how many teams are you working with?
Yeah, so we've worked for a number of different sports. I would say between 3 and 5, and there are a bunch of different teams that we've worked for. And we try to apply this type of methodology, but these teams don't always come with the same problem to us.
Okay, can you please explain why you haven't used survival analysis approach? It allows censoring, while its features could depend on time as well and could be defined in the same manner as in your approach.
Yeah. Very good question. Something we debated a lot in our team. One thing we struggled with survival analysis was the feature selection. So especially in in the Python, but even in the R world, there are L1 regularized versions of survival analysis models available, but they tend to not really work with very high dimensional feature spaces. That's just one reason. And the other reason was, it's actually not that trivial to put time varying coefficients then also in this L1 penalized survival model. So that's another reason. We didn't want to build that algorithm from scratch. We wanted to kind of leverage what was already out there. And that's also why we didn't decide.
Have you tried neural networks?
Again, a good question. So this is something many people ask, oh, why don't you apply like an RNN to like the player tracking data, this kind of stuff. We opted for a simpler approach because in the end, you need to hand this model over to that team as well. So if you give them a very complex model, it might work better, but they might actually not be able to run it themselves. And this was a problem with this client. Like they didn't necessarily have the right capabilities in-house to further deploy this. So we took a conscious decision to not build the most complicated model out there, because if we did that, the project would be doomed to fail from the start.
And finally, insurance companies, have they shown any interest in your work?
Insurance companies. Not that I know of, but I'm sure that this will be of interest to them as well.
Okay, Thomas, thank you.
No problem.
Here's your certificate.
Thanks very much.
Yeah.